Okay, so please, you may start.
Okay, thank you for the introduction, and thanks to Jonathan for the invitation to speak here. I'll be spending some weeks in Warsaw next June, so I'll have more chance to talk with you. So today I want to talk about expansive algebraic actions, and particularly about homoclinic points. So first, let me begin with a very simple example. That is the cat map. It's one of the basic examples in dynamical systems where you take a torus and you take a matrix and you multiply by the matrix and then take a mod 1. So this is very classic example, and it kind of has all a lot of nice properties that people in dynamics like, from topological, geometrical, measure theoretical, algebraic. So it's kind of like in the center of many areas of dynamical systems. So one of the tools that people use to study the hyperbolic toral automorphisms, like this one, are the homoclinic points. So a homoclinic point is a point such that the orbit converges to the identity going forward and going backward. So here I'm taking n as goes to infinity, but also as n goes to minus infinity. Okay, this notion comes from a Poincaré it's in a famous paper in Acta Mathematica when he was studying the three-body problem. And in this particular case, it's not that difficult to show that there exist homoclinic points for hyperbolic toral automorphisms, and this is done geometrically by taking the foliation, the stable and the unstable foliation. So in this particular case, it's not very difficult to prove the existence of homoclinic points, and actually they are dense in this example. Okay, so I'm interested in which ways we can generalize these kind of examples. So one way is the geometrical one, and this is kind of like the also of diffeomorphisms, and here it's kind of like a geometric generalization. But the one I'm more interested in this talk is expansive algebraic dynamical systems. So what I mean by algebraic dynamical system, here we mean that did somebody ask a question? No. Okay.
Please continue.
Okay. When I say algebraic, it means like you have a group that you have X that is a compact abelian group. So for example, in the previous example, X, the torus, is a compact abelian group, and we have an operation in the torus. We have adding mod 1, and so we want this operation to respect the group structure, the T. So we want this to be a group automorphism. So this just means that if we apply T to X plus Y, we get TX plus TY. So in the hyperbolic toral automorphism, T is a matrix multiplication, so obviously it satisfies this property. Okay, but now let me show you another example that it's a bit different. So this is a Ledrapierre's subshift. So we take the configurations of 0, 1 in the lattice, such that if I take a point and I add the two neighbors, the one that is above and the one that is to the right, and I take mod 2, I get 0. So more or less, these configurations look like this. We have zeros and ones. And every time we have 3 dots like in an L shape, like these ones, and we add 1 plus 0 plus 1 is 0. As you can see, you will never see 3 ones in these positions, or a single one, because it does not add to 0. There's always either 3 zeros or 2 ones. So this is the restriction we have. Okay, so this is this XL. This is also a compact group. We simply add each coordinate mod 2. Okay, so this I mean, this is very, I mean, okay, if you take 2 points and you add them, you can simply change the mod, and so it's easy to check that if you add 2 elements in XL, the element will also be in XL, because it will also satisfy this this equation here. So this is right now it's not very clear that this is a dynamical system, and actually it's not a dynamical system in the classic sense. It's this dynamical system in the sense of group actions. So a continuous group action is kind of like a product of a group and a topological structure. So it's a function that goes from gx to x. In general, we will denote this by using this dot. So this is the element on the group, and this is the element on the topological space. And for an action only has 2 properties. One property is the identity times x gives you x. The other one is this kind of associativity that, and this plus is on the group G. So we have this. It's the same to act H and then G than to add G plus H and then act on X. Okay, so it's for example for C actions, there's a correspondence between functions and actions. So you can generate the whole action if you only have one function. And if you want to study for the group set 2, it's kind of like studying 2 commuting transformations. Okay. And now this is kind of a topological. And now if I want to put more algebraic structure, so it's similar. Now we ask again to X to be a compact abelian group. And we want that for every G, this function is a group automorphism. Okay, so and in the particular case of a subshift, the action is given by the translation or the shift set 2 acting on XL. And so the 2 generators are the shift to the left and the shift down. Okay, so this and well, this requires a proof. And the proof, it's simple. All you have to do is check that if you add 2 elements and you shift them by this vector, is the same as if you shift one element and you shift the other element and then you add them. This is also simple algebra to check. Okay, so this action is expansive. That means there's an epsilon such that any 2 different elements will be separated. But actually, this is kind of weird because it doesn't have a homoclinic points. So, but I haven't tell you what's a homoclinic point in this for subshift. So this is only the definition for set 2 shifts spaces. So a point is a homoclinic point if there exists a finite set such that outside that finite set, everything is 0. So in the particular, the point with all zeros is obviously always a homoclinic point, and the point with all zeros is here. The point with all zeros is in this XL, but what I'm saying is it's actually the only homoclinic point, because what happens if you have a boundary where all is zeros? Then you take you start constructing. You start using these three dots to start building what's inside the boundary, and you will see, since you have two zeros, the other one has to be a zero and a zero and a zero and a zero. So it's kind of determined. If you have a boundary with all zeros inside, there can only be zeros. Okay, this is not this does not always happen, because you can have algebraic actions with homoclinic points, but I'm just saying that this is something that doesn't happen in the, for example, for an also kind of so there's ways to build a bit more complicated examples. So for example, if you take any power series, in this particular case, I'm going to take a power series of and the function is at 2 variables, but you can have more variables, and actually your variables can be inside a group, but for now let's just say we have some variables, and we have a power series which is just a polynomial, but you're allowed to take negative exponents. Okay, so I can write this power series like this, and then I can associate to this power series, I can associate a space, a topological space that is XF, and this is and now instead of 0, 1 on each coordinate, I have a torus and a circle. Sorry, I have a 1 torus on each coordinate, and now I also impose some algebraic equation. In this case, I'm going to associate something that is related to this power series. So in the first case, there's a 2, so I put a 2 here, and there's 2 zeros, so I only put X and L. Then I have a negative sign, so I put a negative sign here, and P has the power has 1, so I add a 1 to K, and the other one is 0, so I just leave L. The next one is also negative, so I put negative sign here. But now I have a -2 here, so I write L -2. So basically, this is only 3, but there could be 4 or 5. There could be many positions, and the weight could change. You can have negative or positive weight. So there's a lot to play around here with the power series. And so you obtained here a space, and the shift.
Felipe, there is a question, please.
Yes.
I asked what is mod 1.
So mod 1 is because I want this to so it's kind of, the mod 1 comes from here. It's just like if you add something that gives you, for example, 1.5, you only write 0.5 because you want to stay on the circle.
Okay.
Mm-hmm. And so now again we take the shift action, because now we have a configuration, we have a lot of elements on the circle, and we can move them. We can translate by set, and again you can also check that this is algebraic. And so some examples will have homoclinic points, some will not have homoclinic points. So we are kind of interested in this. And actually there's generalizations. If you take group rings, you can also construct other algebraic actions.
But Felipe, why are you interested in homoclinic points? I didn't understand that.
Why what?
Why are you interested in homoclinic points?
Okay, so Personally, I'm interested in homoclinic points because I'm interested in Gibbs measures. But I think people have other motivations. But for me, the main thing is that you need the homoclinic points to understand thermodynamic formalism. If you want to understand how measures of maximal entropy or equilibrium measures behave, if you have a homoclinic points, you can give a better description of equilibrium measures using the homoclinic points. But I think people in hyperbolic dynamics, they're interested in other things about homoclinic points. Okay, so I haven't defined the homoclinic points in this generality, but I will only do it for finitely generated groups. Okay, so finitely generated just means there's a finite set such that every element can be written as a combination of this finite set. And so given an algebraic action, we say X is a homoclinic point if the limit as G goes to infinity. So G is the size of the smallest path to G using the finite generator. So in other way, in any way you escape, in any way you escape, you converge to the identity. Okay, so this is kind of like in any direction you want to go, you always this is a homoclinic point in this situation here. So the identity is always a homoclinic point, but actually finding other homoclinic points is it can be complicated. And I think maybe these papers, Lind-Schmidt and Chung and Lind, they're not so much interested in the thermodynamic formalism. I think they are more interested in just like what kind of algebraic tools you need to prove homoclinic points. I think that's the main reason. I mean, they don't state a clear motivation, but in order to find the homoclinic point, it's for this algebraic actions, it requires it's kind of some work. It's not that simple. But I mean, there's one way that is easier to find homoclinic points, and this is if you have this shadowing property that I will explain what it is. Yeah. Okay, so let me go back to hyperbolic dynamics. So one of the properties of the hyperbolic toral automorphisms is the shadowing property. So I will state it in generality for group actions. So if we have a sequence of elements indexed by the group, and we have a point set, we're going to say that this point is similar to this index if it follows this, if this is similar to an orbit. So if G Z and WG are very similar. So we say that WG is a pseudo orbit, delta pseudo orbit. It's kind of like if it's locally behaves like an orbit. So these elements only if I put S, and S is the finite generators, and I move along, WG is the same as having WSG. So this is now an element here. So first, so let me give the motivation in G equals Z. So here our generator is only adding is 1. So and a pseudo orbit just means we have a sequence of points, and what we want is if we apply T of WG, we get something that is very close to WG plus 1. So it's kind of, we have some points that kind of that each point, if you map T, it's similar to the next point. And epsilon traces means that there's an actual orbit that is close to this. So an action has is shadowing or has pseudo-orbit tracing property if for every epsilon there exists delta, such that every pseudo-orbit that is good in terms of delta can be epsilon traced by some point x. So it's kind of going from local. So pseudo-orbit is kind of like a local property, and epsilon traces is a global property. So if a pseudo-orbit is good locally, it's going to be good globally. This is what shadowing means.
I believe it does not depend on the choice of the generator.
No, it doesn't. Okay, so this, I mean, there's like the very simple examples that have shadowing are shifts of finite type. Shifts of finite type, they always have shadow. So, and also hyperbolic toral automorphisms, they have shadowing. And the shadowing is a strong property. I mean, it's not something you usually get. It's a strong property that helps you prove several things. So considering that for algebraic actions, finding homoclinic points is very hard, but maybe it would be easier if we could prove that expansive algebraic actions are shadowing. So this was a question of Tom Meyerovich. And by simple, here he meant polycyclic, which is kind of abelian or extensions of abelian groups. So he's asking, okay, at least if the group is kind of simple, can we say that the actions are have this kind of hyperbolic topological hyperbolic property? And actually, this is turned out to be false. So some years ago, Bhattacharya constructed an example of a polycyclic group such that and an action that was expansive but did not have a shadowing property. So we checked this example, and this example has several pseudo-orbits that can be shadowed. Not all of them can be shadowed, but we realized that it almost had the shadowing property. So we defined the following that is called Markovian pseudo-orbit, and this actually this kind of Markovian pseudo-orbits also appear when you study kind of supports of some equilibrium measures. These Markovian pseudo-orbits also appear. So we are going to say that WG is Markovian. So this is kind of this index, this sequences index by the group. We're going to say that this is Markovian if there exist 2 points, x and y, and a finite set, such that WG is equal to x inside A and is equal to y outside of A. So in a sense, it only has finite jumps. This pseudo-orbit only has finite jumps. Previously, we could take pseudo-orbits that every time there's a jump to kind of like to a different here. It's almost an orbit, but it's kind of an orbit that you construct from 2 points, and the jumps are only finite. There's only a finite. So inside it looks like X, outside it looks like Y. And so we define this strong topological Markov property if every Markovian pseudo-orbit can be shadowed. So this is a weaker property because before we wanted all the pseudo-orbits to be shadowed. Now we say, okay, maybe not all pseudo-orbits can be shadowed, only Markovian pseudo-orbits can be shadowed.
Why did you call it Markovian?
We call it Markovian because this is related to something called Markov fields. So Markov fields are, so people wanted to define Markov chains for other groups, for example, set 2. What does it mean to be a Markov chain, or kind of have Markov chain properties when you on for example, on a group action? So the property you get is called the Markov field, and what Markov field means is that if you fix a boundary, whatever you see, the relative probability of what you see inside does only depends on the near on the boundary, does not depend on far away points. So this is and then if you take the support of a Markov field, you get something with this property here, which we call it topological Markov. So it's kind of like the support. It's kind of like when you have a Markov chain, the support is a shift of finite type. And when you have a Markov field, the support may not be a shift of finite type, but the support is will have the topological Markov property. Okay, so here's the first result. So I take G to be essentially amenable. So essentially amenable is basically whatever you can construct using abelian groups. So you take extensions, factors, and inverse limits of abelian groups and subgroups. You can take subgroups of abelian groups, and whatever you get of this family. So it's kind of like the groups that you can construct algorithmically starting from abelian groups. Those are the essentially amenable groups. And so what we prove is that for these groups, and particularly this family contains the polycyclic groups, every expansive algebraic action has the strong topological Markov property, which we shorten like this. Okay, so remember that Bhattacharya had an example that was not shadowing. So it means it's so we may not have shadowing, but we still have this property.
I have a question because there is a very known class called elementary amenable. So what is the difference between element?
Yeah, it's the same. It's the same.
Oh. Okay.
Yeah, it's the same. Yeah, actually, probably I wanted to write elementary amenable.
Okay.
Yeah, I think I think it's not. It's usually elementary. Yeah, not
right.
Essential. No, actually, it's not that they have two names. It's a mistake. It should be elementary here.
Right, because there was this famous article by Chow in 1980 where he introduced this class.
Yeah, that's the one. Yeah. Okay, and then so here's another result. If you have an algebraic action with a strong topological Markov property, then homoclinic points are related to positive entropy. So you will have a non-trivial homoclinic point if and only if the action, and here you take as a measure, you take the hard measure on the group here. This has positive entropy. So it's okay. So actually, this result is a bit more general, but I didn't want to state it in the. This result can be stated purely topologically, but instead of homoclinic points, we use asymptotic pairs. You can use asymptotic pairs, and you can show that if you have the topological Markov property, then asymptotic pairs are related to entropy. Are related to entropy. Okay, so in this case, we only want the homoclinic points. So I mean, if we combine these two, if we combine these two results, what we get is that if you have an elementary amenable group, and you have an expansive algebraic action, there exists non-trivial homoclinic points if and only if the group action has positive entropy. So our conjecture is that we do not need elementary amenable, that this should be true for all amenable groups. Also our conjecture is that when the group is not amenable, the result should be false. But this we also don't have we don't have a counter example. But our conjecture is that there should be, for example, if you take the free group, there should be a counter example. There should be an example with positive entropy, but no homoclinic points.
Can you say more than just existence, structure, cardinality? I don't know.
Sorry, what's your question?
If you can say more than just existence.
Yes. So okay, so I didn't write. Okay, so let me tell you this result, and then I'll tell you a bit more about I didn't write it here, but I'll tell you a bit more. Okay, so here's another result that we can prove. That is that if you can characterize when the action is a K-system. So K-system is Kolmogorov. It means like the entropy is positive with respect to every cover, no, not every cover, every partition. Or it also means this kind of satisfies some kind of Kolmogorov 0-1 law. So in this case, when you have a K-system, this is exactly when the homoclinic points are dense. Okay, so we have kind of these two extreme cases. Here we only want one homoclinic point, non-trivial, and here we want like homoclinic points are everywhere around. So now if we wanted a structural result, or like kind of So for this, actually, you can use entropy. You can use entropy pairs, and so I didn't want to talk too much about them because I'm planning to talk about them in June for the Simon semester. I'll give a short mini course, and I wanted to talk about local entropy. So it's kind of like finding the local version of where the entropy is. And actually, when you have you can find a relationship between homoclinic points and entropy pairs of the related to the identity. So that's kind of like the most we can say, that we can relate the homoclinic points with the entropy pairs related to the identity. That kind of result generalizes this. It's kind of like to put these two statements in one single. So probably, so my plan was to give actually more details in June, and actually maybe give some proofs. But that's kind of like if we really want to find where the homoclinic points are, it's kind of like we need to know where the entropy pairs are. So okay, so this corollary is not entirely new. So this was done for set D by Doug Lind and Klaus Schmidt, and it was also done for polycyclic groups by Chung and Lee. And actually, the three proofs are quite different. For set D, you have a abelian group, so it's kind of like a commutative algebra kind of stuff. So the Chung and Lee, they also prove the result, but they prove it directly, and then they need to use some non-commutative stuff. So actually, their proof is more complicated than Lind-Schmidt, and this new proof is different because it uses this. This new topological property for the actions. Okay, so this okay, so this is what I wanted to say. So I wanted to be kind of like maybe introduction to some other things I want to talk about June. That is, it's kind of in June I want to talk about the local version of and other. I mean, in June I want to give an overview of what's this local entropy theory and how you can state these results in terms of local entropy.
So this is the end of the talk?
Yeah, yes.
Are you aware of the fact that our seminars are 1 hour and a half?
No, I didn't know that.
So the case system means positive entropy for every finite partition, right? Yeah.
Okay, no, I thought it was 50.
Equivalent definitions for those action of Z plus. So that's why I ask what definition of case system is the most useful.
So sorry, I couldn't hear the comment or the question.
You need to speak up because the
No, I just asked about definition of case system used here.
The definition of case system. So it means you can define entropy for a partition.
Okay. So for all finite partitions, it is
yes.
positive. Okay.
Yeah. Mm-hmm.
Absolutely positive.
Or equivalently, you can also say every factor. Every factor of the system has positive entropy. Every non-trivial factor. I mean, because you always have a factor.
So you said that you will say something about the structure of the non-trivial homoclinic point in the case of your result.
So so the structure that I can say, so for this I will have to do the entropy pairs. So the structure is that the homoclinic points, if you take the closure of the homoclinic points, you exactly get the points that are entropy pairs of the identity.
What are entropy pairs?
Yeah, so
You didn't define it.
I didn't define this. So I didn't define this.
But he will define it in June.
So that's like,
yeah, 10 months. You have to wait 10 months. Yeah, if I knew it was okay. No, wait a second. I can define. So I mean, since I have a time, let me define the. I can do this.
Yes, please.
Just
no. Questions?
No, it's now. But I think maybe Michał had a question because he appeared. Michał, do you have a question?
No.
No, I don't have any questions.
Okay, so no, actually the talk is not over.
Don't go away. Don't go yet.
Okay, here's the second part of the talk. Okay, so let me talk first about topological entropy, which actually I haven't. Okay, so this is you can define topological entropy for a open cover, and then you take a topological entropy. It's just supremum over the entropy of the covers. So actually, I mean, in my for me, I'm not that interested in what's the entropy of a particular system. I'm more interested in understanding the differences between having positive entropy and zero entropy. So this is kind of like if you have a system of with positive entropy, and say you ask, okay, where is the entropy of this system? How can you answer this question? So this is, and actually the answer is not something the answer is not in X, but the answer is on X squared. So it's something about how different regions relate. Okay, so we say an open cover is standard if U and B are not dense. So I don't want dense sets. I only want non-dense sets. And now we say a standard cover separates X and Y if we have if Y is not in the closure of U and X is not in the closure of U. So it's kind of and here, so we say X is an entropy pair if for any standard cover that separates X and Y, we will have a positive entropy with respect to this open cover. So this was introduced by Blanchard in the 90s. So if you take the entropy pairs and the diagonal of x squared, you get a closed set. Okay, so this we write ext or egx in terms of an action. So obviously, if you have an entropy pair, the topological entropy with respect to this open cover is positive, and hence the entropy with has to be positive. But actually, the other direction is also true. That if you have a system with positive entropy, then you will find a non-diagonal entropy pair. Okay, so in some sense you can localize the entropy. You can say, okay, between these 2 points, there's a lot of movement that is creating entropy. Okay, so here's an example. Take a disjoint union of the circle, and so we have 2 circles, and we have the doubling map on each circle. And AB is a standard cover that separates points. And this cover has 0 entropy because there's no interaction between A and B, because these are 2 separate covers. So actually, so we have this. So I mean, because the orbit of A will not intersect the orbit of B. So once you want to calculate entropy, you will find that there's no entropy. So this means that if you have 2 disjoint systems like this, the entropy pairs are kind of disjoints. So you have the entropy pairs within A and the entropy pairs within B, and that's it. So there's no interaction. And well, actually, the other thing I'm not proving is that on each doubling map, every pair is an entropy pair. But this you can prove it. Okay, so this is like a very simple example. And then you have the extreme. The extreme is when, so it's when every pair is entropy pair. And this is uniform positive entropy. So it's kind of like the case systems that I defined, but this is just the topological version. Okay, and here, if we have an algebraic dynamical system, an entropy point are the points such that X and the identity is an entropy pair. Okay, so I already, this is and this is kind of like the homoclinic points, but now here we have pairs. So we want the limits of X and Y to be, it's kind of like on the forward, on backwards, or on any direction, actually, they kind of converge. So here's here's the local version. So it's not a structural result. It's kind of like a local version. Maybe the only structural result is about the dense, the case when it's dense. But what you have is that the asymptotic, and look, in this result, there's no algebraic thing. This is like a purely, so I take the asymptotic pairs, which are the pairs that converge to each other, and I take the entropy pairs, and so what we have is that the closure of the asymptotic pairs is equal to the entropy pairs. Okay, so and this is kind of like and from this result, and from this result you can get Okay, so this is the algebraic version. So for a large class of finitely, and for large class, it means elementary amenable groups, you will have that the entropy points are the closure of the homoclinic points. So this is kind of like the local version of the results. Okay, so now actually, and okay, so the other thing I can say is that uniform positive entropy for algebraic actions, if you have uniform positive entropy, it means that the measure is K. So this is the only ingredient missing to get the result I stated before.
Could you repeat it? What was the last result you mentioned? If
Okay, so I'm saying that for an algebraic action, if every pair is an entropy pair, then the Haar measure has the K property. So in this case, there's a relationship between the topological and the measure. Because that's what I stated in my other slides, that the measure, that the homoclinic points are dense if and only if the measure is K. So for example, if the homoclinic points are dense, it means that this thing is the whole space. And if this is the whole space, then it means you have uniform positive entropy. And if you have uniform positive entropy, then the Haar measure is going to be K. Okay, so now I think it's now maybe this is the second ending of the topic.
okay, so let's think. Are there any other questions? Maybe from
People online.
Okay, I see
We
people.
ask a question. Okay.
Okay, if there are no questions, let's thank
everybody. You are invited to the common room for the floor, and I have a cake.
Okay. Thank you, goodbye.
And you are the speaker next.
Yeah, makes sense. Yeah. Unless you want to find someone else.
We